A first course in graph theory. With Science Solution, Arif Nawaz is here. This lecture is about graph basics, simple graph, non-simple graph and types, subgraph and types, connected and disconnected graph. Definitions and examples. Graph. Definition. A graph G consists of a pair V of G and X of G, where V of G is a non-empty finite set whose elements are called points or vertices, and X of G is another set of unordered pairs of distinct elements of V of G. The elements of X of G are called lines or edges of the graph. Now we define order of a graph G. The total number of vertices in a graph is the order of the graph, denoted by mod of G. Now, what is size of a graph G? The total number of edges in a graph is called the size of the graph, denoted by S of G. Here a simple graph is shown in Fig, which has 4 vertices A, B, C and D and 3 edges A to B, A to C and A to D. If X is the line, that is the join of U and V, the points U and V are said to adjacent if X is equal to UV. We say that the points U and the line X are incident with each other. If two distinct lines X and Y are incident with a common point, then they are called adjacent lines. A graph with P points and Q lines is called a PQ graph. Note: if no confusion, we can simply write V of G as V and X of G as simply X. For example, V is the set of vertices A, B, C and D, and X is the set of edges A to B, A to C and A to D of graph G, which is a 4-3 graph, means that there are 4 vertices and 3 edges in this graph. This graph can be represented by a diagram as shown in Fig 1.1. In this graph, the points A and B are adjacent, whereas B and C are non-adjacent. What are adjacent vertices? Adjacent vertices are those vertices which are joined by an edge. Otherwise, they are non-adjacent vertices. Simply, we say that two vertices are adjacent if there is a common edge between them. Adjacent edges. Similarly, two edges are adjacent if there is a common vertex between them. Incident. If two vertices U and V are joined by an edge E, then U and V are incident with E, and so. Loop. An edge joining a vertex V to itself is called a loop. In this case, the vertex V is said to be self-adjacent. In this diagram, at vertex 1, this is the loop. Parallel edges can be defined as if two vertices are joined by 2 or more than 2 finite number of edges, then that edges are called parallel edges. Parallel loops. 2 or more than 2 edges joining a vertex to itself are also parallel, which are called parallel loops. In this diagram, the upper graph has a loop. A single vertex has an edge whose starting and end point on the same vertex. So this is called a loop. And at lower graph, we see more than 2 edges are joining 2 vertices. So these edges are called parallel edges. Now we define simple graph and non-simple graph with types. Simple graph. A graph which is free from loops and as well as parallel edges are called simple graph. Otherwise the graph is non-simple. It means that in a graph, if there are no loop or parallel edges, this is called simple graph as shown in this fig. Otherwise, if a graph having loops or parallel edges, then that graph is called non-simple graph. A non-simple graph is of 2 types. One is multigraph, defined as A graph which has only parallel edges. They also can be parallel loops, and no single loop is called multigraph, as shown in figure. We see there are parallel edges and having parallel loops, but no single loop. And the second type of non-simple graph is the pseudograph, defined as a graph which has only loops with at least one single loop, or a graph which has both parallel edges and loops with at least one single loop. We see this type of graph by diagram. These graphs contain single loop as well as parallel edges and loops. So, single loop must contain in this type. Here we have two remarks. Let G be a graph of order n and size S of G, then the maximum size of a simple graph G is NC2, and the second remark is if size of G is less than or equal to NC2, then G can be simple graph, but if size of G is greater than NC2, then G cannot be simple. Subgraph. A graph H is said to be a subgraph of a graph G if and only if V of H is the subset of V of G and E of H is the subset of E of G. Means that the vertex set of graph H is the subset of vertex set of graph G and edge set of graph H is the subset of edge set of graph G. Further we explain subgraph by an example. Let G be a graph having 5 vertices and 6 edges as shown in fig. Then subgraphs can be H1, a graph of only 3 vertices having no edge, and the second subgraph H2 having 4 vertices and 3 edges. G3 can be another subgraph of G of 4 vertices and 4 edges, and G4 is also a subgraph of graph G, where G4 is the subgraph of G of 4 vertices and 3 edges. In another way, definition and example of a subgraph. A subgraph can be defined as let G be a graph of set of vertices V and set of edges E, and H is the graph of set of vertices V1 and set of edges of E1. We say H is a subgraph of G if and only if V1 is the subset of V, means that set of vertices of H is the subset of the set of vertices of G, and E1 is the subset of E, means that set of edges of subset H is the subset of the set of edges of G. For example, here diagram of a graph G is shown that there are 5 vertices V1, V2, V3, V4 and V5 and 5 edges. If H is another graph having only 2 vertices V1 and V2, which is actually the subset of the set of vertices of G, and the edge set of graph H is equal to 5 because the graph H having no edge. Hence, we see the set of edge of graph H is the subset of edge set of graph G. So, the graph H fulfill both two conditions of subset, being a subgraph of a graph G, then H is the subgraph of a graph G. Now we discuss the definition and some examples about induced subgraph. Let G be a graph having set of vertices V and set of edges E, and H is a graph having set of vertices V1 and set of edges E1. We say H is an induced subgraph of G if and only if first condition is H is a subgraph of G. Second condition is E1 belong to E1 means K edge 1 contain in the set of edges E1 if and only if edge 1 will also contain in E. In other words, if two vertices are connected by an edge in the original, they must also be connected by an edge in the subgraph. Here some examples are shown with diagram which makes easy to explain subgraphs and induced subgraph. Spanning subgraph can be defined as let G is equal to V, E and H is equal to V1, E1. We say H is a spanning subgraph if and only if V1 is equal to V and E1 is subset of E. In other words, the spanning subgraph has to have all vertices of the original one. For example, let G be a graph having four vertices V1, V2, V3, V4 with 5 edges as shown in diagram. If we make another graph H by these four vertices in such a way that two edges which are joining V1 to V2 and second one is joining V2 to V3 are cancelled out, then we get graph as shown in the diagram. This graph H will be the spanning subgraph but not induced. Now some definitions of graph features can be defined as let G be a graph, then in G between two vertices starting from U to V we have walk. Walk is an alternating sequence of vertices. Trial. Trial is a walk without repeating any edge. Path. Path is a walk without repeating any vertex. Circuit. Circuit is a closed trial. Start and end are same. Geodesic. Geodesic is a shortest path between two vertices. Detour. Detour is a longest path between two vertices. Cycle. Cycle is a closed path. K-cycle. K-cycle is a cycle of length k. Odd or even cycle. Odd or even cycle is a cycle of odd or even length. Triangle and square is a 3-cycle and 4-cycle respectively. Girth. The girth of the graph is the length of a shortest cycle in G, denoted by W of G. Length. Length is the number of edges in a walk. Now we discuss these features by examples with diagram. A graph G is shown in Fig, whose set of vertices is U, V, W, X, Y. Then in G, X to Y, Y to W, W to V, V to Y, Y to W, and W to X is a walk of length 6, also closed. Let's see a trial of length 5. We start from vertex U, U to W, W to Y, Y to X, and X to W, then W to V. This is a trial of length 5. Then also we see a path of length 4, W, Y, V, U to W. is a path of length 4. Then and UWYXWVU is a circuit of length 6. UVYXWU is a cycle of length 5. 5 cycle, odd cycle. We also have shortest path between two vertices U to W and W to X, which is called a geodesic between U to X. A 3 cycle can be seen starting from W to V and then Y to W is a triangle in G. A 4 cycle X to W, W to V, V to Y, Y to X is a square in G. The girth of the graph G is W of G is equal to 3. The shortest cycle in G is 3 cycle. Now we discuss connected and disconnected graphs. In a graph G, two vertices are connected if there is a path between them. Adjacent vertices can be connected vertices, but connected vertices should not be adjacent vertices. If every two vertices of a graph G are connected, then G is a connected graph, otherwise G is disconnected. A disconnected graph has connected parts as subgraphs, each of which is called a component. The number of components in a graph G is denoted by K of G. A graph G is connected if and only if K of G is 1. The distance between two vertices U and V in a graph G is the length of a geodesic between U and V denoted by D of UV. If there is no path between U and V, means that U and V are disconnected. Then distance between U and V is equal to undefined. The diameter of connected graph G is the maximum distance between two vertices in G, denoted by diam of G. Now we explain connected and disconnected graphs by an example with diagram. We take disconnected graph with K of G is equal to 2. Each of component is a graph. We can easily see G1 is a graph having 6 vertices, which are shown in the graph by green color, which is disconnected to the graph G2 having 5 vertices with blue coloring shown in the diagram. Here we see the vertices of G1 are A, B, C, D, E and F, and the vertices of G2 are U, V, W, X and Y. Now we discuss the distance and diameter between any two vertices in this diagram. The distance between the vertex A and D will be 2, because there are only two edges between the vertex A and D, and the distance between A and Y will be undefined because there is no connection between A to vertex Y. Then distance between F and C will be 1 because there is only one edge between F and C vertices. If we see the distance between F and W, then answer will be undefined because there is no connection between F and W vertices. So the distance between F and W is undefined. Now we see the diameter of G1, which is 2, because we know that diameter of a graph is the maximum distance between two vertices of the graph G. So, between any two vertices, there is maximum distance is 2, and the diameter of graph G2 is equal to 3, because the maximum distance between any two vertices of graph G2 is 3. So I hope you understand.